Tonight, we are going to look at the planet that almost everyone gets wrong. Saturn is the one people point to first, the one in every solar system poster, the one children learn by name before they can name a continent. It sits in the outer solar system with its rings around it, steady and golden, and the word that comes to mind is beautiful. Not threatening, not violent. Beautiful, but that impression is built entirely on distance. And when the distance goes away, everything changes. Most people think Jupiter is the planet to be afraid of, the one with the giant storm, the one that eats smaller worlds. But when you actually examine what Saturn is doing, what is inside it, what surrounds it, and what its gravity has already done to the rest of the solar system, the picture becomes much harder to look away from. By the end of tonight, you are going to understand why Saturn, not Jupiter, not Venus, not any other world we know, deserves to be called the scariest planet in our solar system. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. On a clear night, if you know where to look, Saturn is visible without a telescope, not as a disk, not as a recognizable shape, just a point of light, steadier than the stars around it, golden in color, holding its position in the sky with the patience of something very old and very far away. It is one of the 5 planets visible to the naked eye, known to every civilization that ever kept records of the sky. The Babylonians tracked it, the Greeks named it. Every culture with an interest in the heavens noticed it, catalogued it, and gave it significance. For most of human history, Saturn was simply a light that moved slowly across the stars. Then came the telescope. In 1610, Galileo turned one towards Saturn and saw something he could not explain. The planet appeared to have handles, he wrote, as though something was attached to it on both sides. He had no framework for what he was seeing. It would take another 50 years, and better instruments before the Dutch astronomer Christiaan Huygens worked out what those handles actually were. Rings. When you look at Saturn through a basic backyard telescope, even a modest one, you can see them clearly. A flat disk of material tilted at an angle, surrounding the planet at a distance, catching the sunlight in a way that makes the whole system look like something carefully constructed, something deliberate. That is the impression Saturn gives from here. Deliberate, composed, a planet that has arranged itself into something worth looking at. Most people hold on to that impression. Saturn is the beautiful one, the aesthetic one, the planet that earns a gasp when you first see it through glass. But that impression is not describing Saturn. It is describing distance. Right now, Saturn is roughly 1.4 billion kilometers from Earth. That distance is doing something specific. It is compressing a world of 1,800 kilometer per hour winds, pressure gradients that turn hydrogen into metal, and a gravitational field that actively tears moons apart into something that looks like a golden point of light with a ring around it. Everything that makes Saturn look serene from here is a product of that distance. And distance is about to run out. For most of human history, Saturn was a mystery described only by what the eye could do with it. The Babylonians, who kept some of the oldest systematic records of celestial objects, noted it as the slowest moving of the visible planets, the one that took nearly 30 years to complete a single circuit through the constellations. They associated that slowness with age, with weight, with the kind of authority that belongs to things that change slowly and outlast everything around them. The Greeks connected it with the god of time. The Romans made the association permanent in the name that has held for 2,000 years. In every culture that kept systematic records of the sky, Saturn's slow, deliberate motion across the constellations marked it as different. Not dangerous, different, something that operated on a longer schedule than the faster planets, something more fundamental. That impression of solidity and permanence became the foundation of how Saturn was understood for centuries. By the time Galileo pointed his telescope toward it in 1610, the assumption was that Saturn, like every planet, would resolve into a disk under magnification, slightly flattened perhaps, with some visible surface features. What he saw instead produced a letter that historians still quote for its confusion. He saw 3 objects where one should have been, the planet flanked by something on each side, and he had no category for it. He wrote that Saturn appeared to be accompanied by 2 companions, one on each side, like ears. The companions did not move independently. They did not change position relative to the planet. They did not behave like moons, the way Galileo's 4 Jovian moons moved and changed position. They just stayed there on either side, part of the planet in some way he could not explain. Then, in 1612, they disappeared. Saturn had moved in its orbit to a position where Earth was nearly in the plane of the rings, and from that viewing angle, the rings are effectively invisible. They are extraordinarily thin relative to their width, and when viewed edge-on, they vanish. Galileo, who had no knowledge of rings, was baffled. He wrote that Saturn had devoured its own children, a reference to the myth of Kronos, the Greek equivalent of the Roman Saturn, who consumed his offspring. He died in 1642, without understanding what he had seen. Christian Huygens worked it out in 1655, though he kept his conclusion in an anagram for 2 years before publishing it openly. A flat ring inclined to the ecliptic, surrounding the planet without touching it. When he published the full explanation in 1659, it was the first time a structure of that kind had been described for any astronomical object. The word ring, as applied to a planetary feature, entered the vocabulary. In the centuries that followed, the rings were mapped and subdivided, the gaps within them were identified and named, and their behaviour under different lighting and viewing angles was catalogued. Giovanni Cassini, working at the Paris Observatory in the 1670s, identified the gap between the A and B rings that now bears his name. The Cassini division was the first evidence that the ring system was not a single uniform disk, but a complex structure with internal architecture. None of this early observation gave any indication of what the rings were actually made of, or what was happening inside them. From Earth, through even the best telescopes of the 19th century, the rings looked like a smooth, solid structure. They looked deliberate. They looked as though something had placed them there. That impression lasted until spacecraft showed us the truth. You can still recreate it with any telescope that has sufficient aperture. Find Saturn on a clear night, centre it in the eyepiece, and the rings will be there. Tilted at their current angle to your line of sight, brighter than the disk of the planet they surround. The gap of the Cassini division, visible as a dark line between the inner and outer bright bands. The image that Huygens described, the flat ring inclined to the ecliptic, is the same image you will see. What is happening inside that image is not. The first thing that changes when you look more carefully is scale. Saturn is not big the way a mountain is big, or the way an ocean is big, or even the way a continent is big. Those words belong to things a human being can reach, walk across, or fall off the edge of. Saturn does not operate at those scales. The planet's diameter across its equator is 116,460 kilometers. Earth's is just over 12,700. Put those two numbers side by side, and Saturn is roughly 9.5 times wider than the world beneath your feet. If Earth were the size of a nickel coin, Saturn would be the size of a volleyball sitting next to it. But diameter is only the beginning. Volume is where the scale stops being comparative and starts being difficult to hold. Saturn's volume is large enough to contain 764 Earths, not arranged side by side, stacked loosely in a line you could imagine. All 764 packed inside the same shell that contains Saturn, with room to arrange them. If you removed every person and mountain and ocean from the Earth, flattened it down, and tried to fill Saturn with those Earths, you would need 764 of them before the space ran out, and yet Saturn is lighter than you would expect. This is the first place where the planet starts to feel strange rather than simply large. Saturn's average density is 0.687 grams per cubic centimetre. Water is 1.0. Saturn is less dense than water. In the thought experiment where someone built a bathtub large enough to place Saturn in, Saturn would float. That number tends to stop people. A planet 9 times wider than Earth, capable of holding 764 of them inside its volume, lighter than the water in a glass. The mass is still enormous, 95 times the mass of Earth, but distributed across a volume so vast that the average density falls below the thing you pour from a tap. This happens because Saturn has no iron core filling its centre the way Earth does, no dense rock in a thick crust. Saturn is predominantly hydrogen and helium, gas all the way down, compressed by its own gravity into different and increasingly extreme forms. The gravity at the outer cloud tops is close to Earth's, 1007 times Earth normal to be specific. That number sounds almost survivable. It should not. The gravity that feels familiar at the outer edge is just the beginning of what the inside of Saturn does. And the inside of Saturn is a different world entirely. The mass comparison between Saturn and Earth involves a number large enough to produce a slight cognitive stall when you try to hold it directly. Earth's mass is approximately 5.97 times 10 to the 24th kilograms. This is already a number too large to have any intuitive feel. It is 5,970 trillion million kilograms. The zeros accumulate past any scale the human nervous system was built to respond to. We know intellectually what a kilogram is. We know what a million is, sort of, and a billion is already vague. A trillion is a word, not a felt quantity. Beyond that, the numbers are simply abstract identifiers with different lengths. Saturn's mass is 95.16 times that. The question of why Saturn floats, why a planet 95 times Earth's mass is less dense than water, comes down to composition. Earth is a terrestrial planet, built largely from rock and metal, with a dense iron-nickel core at its centre that contributes significantly to its average density. That core alone is roughly as dense as iron. The mantle above it is rock, also relatively dense. The oceans and atmosphere sitting on top represent a small fraction of the total mass. Earth is, in terms of its interior, a dense iron ball coated in rock and ocean and air. Saturn has none of that architecture. It formed in the outer solar system beyond the frost line, where temperatures were cold enough for ices and gas to condense alongside rock and metal. The early Saturn accumulated enormous quantities of hydrogen and helium, the two most abundant elements in the universe, which happen to be the lightest. The metallic and rocky materials that do exist in Saturn's core are present, but they are buried under and surrounded by vastly more hydrogen and helium than any terrestrial planet contains. The result is a planet that is mostly hydrogen, the lightest element in existence, compressed by its own gravity into different states. but never compressed densely enough at the outer layers to produce anything like rock's density, and never with enough heavy material throughout the interior to bring the average above the density of water. If you could actually place Saturn in water, and if you had a bathtub scaled to the task, it would float, bobbing in a body of water larger than the inner solar system. The image is physically real, even if the setup is not. Saturn's low density also has implications for what happens when you approach it. The planet's gravity is not dramatically stronger than Earth's at the cloud tops despite its far larger mass, because the surface, such as it is much farther from the centre of mass. If you doubled the distance between yourself and a gravitational source, the force you feel drops to a quarter. Saturn's cloud tops are much farther from its centre than Earth's surface is from Earth's centre, and that partially offsets the mass advantage. The result is a surface gravity of 1.07 g, almost indistinguishable from what you experience at sea level on Earth. For about the first few seconds of any descent into Saturn, a human body would feel nearly normal gravitational weight. Everything else would be wrong immediately. The temperature, the pressure, the chemistry, the absence of anything to stand on. But the gravity would feel familiar. The familiar gravity in the alien everything else is a useful description of the trap Saturn sets in its appearance from Earth. The numbers that sound manageable, the ones that land within human experience, are real. And behind each of them is a different number, or a different physical condition. That belongs to a completely different category of existence. The rings, when you first understand what they are, do not immediately feel dangerous. That is by design. The appearance earns the wonder first. Saturn's ring system spans an extraordinary distance. From the inner edge of the D ring to the outer edge of the E ring, the full system covers roughly 280,000 kilometers. That is farther than the distance from Earth to the Moon. When sunlight falls across those rings at the right angle, they reflect it back across space in a band of colour and shadow that has no equivalent anywhere else in the solar system. The rings are not a single solid structure. They are made of individual particles, billions of them, ranging from grains smaller than a grain of sand to chunks the size of a house. Most are water ice. Some contain rock and dust. They orbit Saturn at different speeds depending on their distance from the planet, following the same gravitational rules that govern every object in space, forming into distinct bands separated by gaps caused by the gravitational pull of Saturn's moons. The most visible of those gaps is called the Cassini division. It is a gap roughly 4,800 kilometers wide, dark against the bright rings on either side, and it is there because the moon Mimas pulls any particle that would occupy that orbit into a slightly different path each time they align. The gap is not empty, it still contains material, but it is significantly less dense than the rings around it, and from Earth it looks like a clear dark band drawn through the brightest part of the system. When you understand that billions of individual objects, each following their own orbital path, sort themselves over millions of years into bands precise enough to produce visible geometry, the rings stop feeling random and start feeling organized in a way that earns the word beautiful. They are genuinely extraordinary. That is not a false impression. The ring system is one of the most structurally complex natural objects in the solar system, and the forces that maintain it are the same forces responsible for some of the most elegant patterns in physics. But here is where the crack begins to open. The rings are organized by exactly the same force that tears things apart. The organization is not peaceful. It is the result of gravitational competition happening at every scale simultaneously. The particles that form those clean bands are moving at orbital velocities between 8 and 20 kilometers per second, depending on their distance from Saturn. that is up to 72,000 kilometers per hour. At those speeds, collisions between particles are not gentle. They are impacts. The dust and ice and rock in the ring system are constantly colliding, breaking apart, redistributing, and reforming under the same gravity that organised them. When Cassini, the spacecraft NASA and ESA sent to study Saturn, flew through the gap between the innermost ring and Saturn's cloud tops in the final year of its mission, it measured the particle environment it was crossing. The gap appeared clear from Earth. Up close, it was not empty. There were still particles crossing the spacecraft's path. The mission team had designed Cassini's antenna as a shield during those passes, pointing it forward to protect the more delicate instruments behind it. The rings are also younger than the solar system. The current leading estimate places their formation between 100 and 400 million years ago, which sounds old, but is relatively recent in planetary terms. The solar system is 4.5 billion years old. The rings appeared somewhere in the final 10% of that history. Before they formed, something crossed a line it could not survive. That line is still there. That process is still running. The rings that look permanent from Earth have been building and breaking since before the first dinosaurs evolved. They are not ancient and immovable. They are a collision field that has been running for 100 million years, and the same force that shapes them into visible bands is also, slowly but measurably, consuming them. The Cassini division was not understood initially. When Giovanni Cassini first observed it in 1675, the gap looked like empty space between two rings, and the natural assumption was that the gap was simply an absence of material. Maybe the rings had never formed in that zone, or something had cleared the material out long ago, and what remained was a gap you could look through. The true explanation took almost 3 centuries to work out. The gap is maintained by a gravitational resonance with Mimas. Any particle that would orbit in the Cassini division would have an orbital period exactly half of Mimas's orbital period. That means on every second orbit of a Cassini division particle, Mimas would be in the same relative position, and the gravitational kick Mimas delivers would be in the same direction. Over time, those repeated kicks accumulate, pushing particles out of the resonant orbit. It is orbital housekeeping done by gravity. The gap is not empty because nothing formed there. It is empty because anything that wanders into that orbit eventually gets kicked out. This same mechanism, gravitational resonances clearing orbital gaps and maintaining ring structure, operates throughout the ring system. The Encke gap is maintained by the small moon Pan, which orbits within the gap itself, sweeping the zone clear. The Keeler gap is maintained by the moon Daphnis, whose gravity creates ripples in the ring edges that Cassini photographed in extraordinary detail. Waves in the ring material raised by Daphnis's passage that look, at the scale of the ring particles, like a stone being dragged through still water. The rings are not passively sitting there, they are being actively shaped by the gravity of the moons orbiting around and within them. The moons affect the rings. The rings affect the moons. The particles affect each other. The magnetic field affects charged particles. The whole system is a gravitational machine with many moving parts, and what looks from Earth like a clean band of material is the time average product of an enormous number of individual gravitational interactions happening simultaneously. This makes the ring system one of the most scientifically valuable structures in the solar system for studying orbital mechanics, gravitational dynamics, and the physics of collisional systems. The equations that govern the rings apply to accretion disks around black holes, to the disks of gas and dust that form planetary systems around new stars, to the behaviour of any large collection of objects interacting gravitationally. Saturn's rings are a natural laboratory visible from Earth. an analogue for processes that happen at scales we cannot observe directly. The irony is that most of the people who have ever looked at Saturn's rings have done so without knowing any of this. The beauty registered. The physics did not need to be understood for the beauty to work. And then Cassini arrived and spent 13 years close enough to see the waves in the ring edges and the braided F-ring and the material falling into the atmosphere, and the beauty became something more specific. A collision field that has been running for 100 million years, shaped into visible geometry by the same gravitational forces that will eventually end it. The atmosphere of Saturn is not calm. That needs to be said plainly, without qualification, before anything else about it. The atmosphere of Saturn is not calm. It is not occasionally stormy in the way Earth's atmosphere is occasionally stormy. It is not interrupted by extreme weather events the way a hurricane interrupts an otherwise manageable climate. The baseline state of Saturn's atmosphere is what most other planets would classify as a catastrophic event. At the equator, Saturn's jet stream moves at roughly 1,100 km per hour. That number is a sustained wind speed, not a peak gust recorded during a storm, not the product of some unusual seasonal pressure difference. That is what Saturn's atmosphere does when nothing out of the ordinary is happening. To understand what that means, consider the comparison. The strongest tropical cyclones ever recorded on Earth, Category 5 hurricanes and their equivalent, reach sustained wind speeds of around 300 to 345 km per hour. Those storms represent the upper limit of what Earth's atmospheric conditions can produce, and they are considered extreme events, tracked by satellite, named individually, studied for weeks before and after they make landfall. Saturn's baseline equatorial wind is 5 times that speed. A tornado is a more violent structure than a hurricane, faster and more concentrated. The fastest tornado wind speed ever reliably measured was around 480 km per hour. Saturn's sustained equatorial winds are nearly 4 times that. The Parker Solar Probe, the fastest human-made object ever built, reached speeds of roughly 692,000 km per hour at its closest approach to the Sun. That is a spacecraft, in a vacuum, given the full gravitational assist of the closest star in the solar system. That comparison is about speed through space, not wind speed in an atmosphere. Wind speed is different, because the resistance of the medium it moves through defines how much force it carries. The winds on Saturn are not moving through a vacuum, they are moving through hydrogen and helium gas, and the force they carry scales with both their speed and the density of what they are pushing. Saturn's atmosphere is predominantly hydrogen. At the outer layers, where those 1,100 km per hour winds blow, the density is low enough to be technically comparable to what we would call a thin atmosphere. But thin does not mean harmless at those speeds. A column of low-density gas moving at 800 km per hour carries enough momentum to strip away, shear apart, or simply overwhelm any object introduced into it. This is not a description of what Saturn's atmosphere does occasionally. This is what it is doing right now. There is no weather season on Saturn where the winds slow down and the atmosphere becomes navigable. The planet rotates roughly once every 10.5 hours. Its enormous mass and rapid spin drive a circulation pattern that produces those equatorial jet streams as a permanent atmospheric feature. The 1,800 km per hour wind is Saturn's atmosphere at rest. What happens when it is not at rest is the next part of this. The question of why Saturn's winds are so fast has not been fully answered. The basic physics is understood. Saturn is a gas giant with no solid surface to slow the atmosphere through friction, the way Earth's surface slows our lowest atmospheric layers. The rapid rotation, once every 10.5 hours compared to Earth's 24 hours, drives strong jet streams. The thermal energy in the atmosphere, some of it from sunlight and some of it from heat escaping from the planet's warm interior, powers the circulation. But the details of why the equatorial jet stream specifically reaches 1,100 km per hour, rather than some other speed, why the atmosphere settles into its specific pattern of bands and zones, why the jet streams are as stable as they appear to be over long observation periods, those questions involve atmospheric dynamics that are difficult to model accurately for a planet we cannot sample directly. Jupiter's atmosphere, for comparison, has equatorial winds that are also fast, roughly 640 km per hour. That is faster than any wind on Earth and would be considered extraordinary on any terrestrial scale. Saturn's equatorial winds are nearly 3 times faster than Jupiter's. The difference may be related to the ratio of internal heat to solar heating. Saturn radiates almost twice as much heat from its interior as it receives from the Sun. Jupiter's internal heat output relative to solar input is lower. The proportion of internal heat may drive more vigorous atmospheric circulation on Saturn than on Jupiter. This remains an area of active research. What is known observationally is that the banded structure of Saturn's atmosphere, the alternating light and dark bands visible in images, is a product of those jet streams. The boundaries between adjacent jet streams moving in opposite directions create the visible boundaries between bands. Where Saturn's atmosphere appears calm from Earth, what is actually visible is the upper surface of a circulation system moving at speeds that have no analogue anywhere in Earth's weather history. Cassini's instruments measured wind speeds at various latitudes and altitudes throughout its mission. The data confirmed and extended Earth-based observations. The 1,800 km per hour equatorial jet is real. It is consistent. It has been measured repeatedly. It is not a one-time phenomenon or an artifact of unusual conditions during the observation period. It is Saturn's atmosphere doing what Saturn's atmosphere does. For any object introduced into that environment, the physics is not complicated. At 1,100 km per hour, even a low-density gas column carries enough momentum per unit area to exceed the structural limits of any material currently used in spacecraft construction. The heat, the pressure, and the chemistry would also be lethal long before the wind speed became the primary concern. But the wind speed would be a primary concern. There is nothing gentle about it. In 1980, Voyager 1 sent back images of Saturn that produced, in at least a few of the scientists studying them, a kind of quiet disbelief. The spacecraft had passed Jupiter the year before, had photographed the Great Red Spot and the turbulent cloud bands that most people use when they think of Jupiter as the violent planet. Saturn was expected to be different. Calmer perhaps, more organised. The rings gave it that aesthetic of order. The images from the North Pole did not fit. There was a storm sitting at Saturn's North Pole, and it was not the storm's presence that produced the disbelief. It was the storm's shape. It was a hexagon. Not an approximation of a hexagon. Not a roughly 6-sided structure that scientists squinted at and called hexagonal for convenience. A persistent, clearly defined 6-sided geometric pattern surrounding Saturn's North Pole, with each side of the hexagon measuring approximately 14,500 kilometers in length. Each individual side of this storm structure is wider than the diameter of the entire Earth. The initial reaction among some researchers was to question the instruments. Natural fluid dynamics does not produce regular geometric structures. Fluid systems are governed by turbulence, rotation, temperature gradients, and pressure differences. None of those forces, on their own or in combination, obviously produce a hexagon. The pattern was so regular, so geometrically precise, that it looked more like something drawn than something that had formed. But it was not a measurement artifact. Cassini, which arrived at Saturn in 2004 and spent 13 years studying the system, confirmed the hexagon. It photographed it repeatedly, in multiple wavelengths, over more than a decade of observation. The structure did not dissipate. It did not change shape. It did not shift into something less geometric as more data accumulated. The hexagon was there in 1980 when Voyager first saw it, and it was still there in 2017 when Cassini completed its mission. The central vortex inside the hexagon is its own structure. A rotating storm at the heart of the hexagonal pattern, with winds inside the vortex reaching roughly 500 kilometers per hour. Around the edges of the hexagon, the boundary between the hexagonal structure and the surrounding atmosphere is sharper than fluid dynamics intuitively suggests it should be. A wall of wind that maintains its geometry against the pressure of the atmosphere around it. The leading explanation for the hexagonal shape involves Saturn's rotation. At certain rotation speeds and atmospheric conditions, fluid dynamics can produce wave patterns that lock into standing geometric shapes. Laboratory experiments on Earth, spinning tanks of fluid at carefully controlled speeds, have produced hexagonal patterns in the fluid surface that resemble Saturn's structure. The mathematics is consistent with what we observe, but the precise conditions that stabilize Saturn's hexagon, that keep its walls from degrading into turbulence the way most large storm systems eventually do, are still not fully characterized. The hexagon has been running continuously for at least 40 years of direct observation. Scientists estimate it may have been present for centuries. It sits above Saturn's North Pole, a geometric structure wider than the Earth in each of its 6 sides, maintained by physics that we can model but cannot yet completely explain. There is nothing else like it anywhere in the solar system, and it is not the largest atmospheric event Saturn produces. The hexagonal storm at Saturn's North Pole was not continuously observed between the Voyager flyby in 1980 and Cassini's arrival in 2004. The 2 decades between those visits were filled in only by ground-based observations and, beginning in the 1990s, by the Hubble Space Telescope. Hubble confirmed the hexagon was still there in the 1990s. It was not a temporary feature that had appeared and dissipated between Voyager and Cassini. It persisted through a full Saturn season change, through orbital positions where the northern hemisphere moved from winter into spring, through all the variations in sunlight and temperature that accompany Saturn's long year. When Cassini arrived, it had instruments capable of imaging the hexagon in detail across multiple wavelengths, including near-infrared wavelengths that can penetrate the haze layers and reveal structure at different atmospheric depths. What those observations showed was that the hexagon is not merely a surface feature, it has vertical extent. It reaches from the visible cloud tops downward into the deeper atmosphere by hundreds of kilometers, a column of hexagonal structure rotating in the atmosphere. The central vortex within the hexagon is its own distinct feature. Images from Cassini show the vortex as a spiral of clouds rotating around the pole inside the hexagonal boundary, with cloud structures visible at multiple scales within it. The vortex is a cyclone, rotating in the same direction as Saturn's rotation. At the centre of the cyclone there is a clear eye, a region of calmer conditions at the pole itself, surrounded by a ring of tall clouds that form the eye wall. Earth's polar vortex, the pattern of rotating upper atmospheric winds that plays a significant role in winter weather patterns at high latitudes, is a loosely organised feature that shifts and sometimes breaks down. It is not geometrically precise. It does not form a hexagon. It does not maintain sharp boundaries the way Saturn's does. Saturn's north polar vortex has maintained its hexagonal boundary for at minimum 4 decades of direct observation, and almost certainly far longer. The geometry is precise enough that when laboratory fluid dynamics experiments produced hexagonal patterns in rotating fluids under the right conditions, the match to Saturn's structure was immediately recognizable. The experiment is this: fill a large circular container with water. Place a smaller rotating cylinder at its center, spin the outer container at a fixed speed and the inner cylinder at a different speed. Under the right speed ratio and fluid depth, the boundary layer between the two rotating systems develops a wave pattern that locks into a polygon. Triangles at some speeds, squares at others, pentagons, hexagons, Saturn's atmosphere, in the region where the hexagonal storm boundary sits, appears to be running a version of that experiment at planetary scale, with the differential rotation between the polar vortex and the surrounding atmosphere providing the two rotating systems, and the atmosphere providing the fluid. The physics works. The geometry emerges naturally from the physics, and it has been running in Saturn's atmosphere since before the earliest written human records, since before the civilizations that first noticed Saturn as a point of light in the sky, since before our species learned to write down what it observed. It has been rotating at Saturn's north pole for all of recorded human history, and it will likely still be there long after everything in this recording has been forgotten. Every 29, 5 years, once per Saturn year, something breaks loose in the deep atmosphere. It begins as a white spot, a bright eruption of material in the northern hemisphere, usually, pushing upward through the cloud layers into the upper atmosphere. The spot grows. Within weeks it starts to elongate, stretching eastward along Saturn's atmospheric bands, carried by the same jet streams that normally maintain the planet's visible structure. Within months, the storm can encircle the entire planet. These events are called great white spots, and they have been observed on Saturn for as long as astronomers have been able to watch the planet carefully. There was one in 1876, and another in 1903, and again in 1933, 1960, and 1990. The intervals are not perfectly regular, but they cluster around Saturn's year. The storms appear to be a feature of Saturn's seasonal cycle, driven by changes in sunlight absorption at different latitudes as Saturn completes its long orbit around the Sun. The most recent one occurred in December 2010. Cassini had a front row position. The 2010 Great White Spot began as a white spot roughly the size of Earth. Within weeks it had grown into a complex storm system. Within months, the storm's outflow had wrapped around Saturn's entire northern hemisphere, forming a band of disturbed cloud material stretching across the planet in both directions from the original eruption site, the leading edge eventually catching up with and colliding into the trailing edge to form a closed system. The scale of the disturbance from the 2010 storm extended into Saturn's stratosphere. Temperature readings from Cassini showed that the stratosphere above the storm warmed by hundreds of degrees as heat and material pushed upward from the lower atmosphere. That warming persisted for years after the visible storm features had faded. The planet's stratospheric structure was still recovering from the 2010 event when Cassini ended its mission in 2017. For comparison, the largest storm systems on Earth, the most extensive patterns of connected atmospheric disturbance, cover perhaps a tenth of the planet's surface. A great white spot on Saturn can wrap around the entire circumference. These are not unusual events. They are not disasters interrupting an otherwise stable system. They are scheduled. They follow Saturn's calendar. They are part of how the planet breathes. And underneath all of it, under the hexagonal polar vortex and the equatorial jet streams and the great white spot that is already building again somewhere deep in the atmosphere, the interior of Saturn is something else entirely. The 2010 storm was not an anomaly. The next one is already building somewhere below the visible cloud tops, timed to the planet's own calendar, and it will come whether or not anyone is watching. The 2010 Great White Spot gave scientists something that the earlier observations from Earth-based telescopes and the brief flybys of earlier spacecraft had never provided: a front-row view from a spacecraft in orbit. With instruments capable of measuring temperature, composition, and dynamics across the full extent of the storm. Cassini was not positioned for optimal viewing when the storm began. It was on the opposite side of Saturn. But the team realigned the spacecraft's observation schedule and began systematic coverage of the storm within weeks of the initial eruption. Over the following months, as the storm grew and encircled the planet, Cassini tracked it from orbit. What the spacecraft's composite infrared spectrometer measured in Saturn's stratosphere was startling. The temperatures in the stratosphere above the storm's anvil region, the highest part of the storm cloud system, rose by hundreds of degrees relative to the surrounding stratospheric temperature. This warming was not expected. Normally, Saturn's stratosphere is cold and stable, far above the main weather layer. The 2010 storm punched material from deep in the troposphere upward into the stratosphere, with enough force to heat that layer significantly. Saturn releases internal heat generated by the slow gravitational contraction of its interior and by the differentiation of helium settling downward through hydrogen. That internal heat is one of the factors driving Saturn's atmospheric dynamics. The Great White Spot appears to be one of the mechanisms by which that internal heat is released in a concentrated burst, when the slow build-up of convective instability in the deep atmosphere finally exceeds the stable layers above it and erupts through. After the 2010 storm's visible features dissipated, typically over a period of months as the storm material was sheared apart by the jet streams and spread around the planet, the stratospheric warming persisted. It was still measurable in Cassini's data years later. The storm heated a layer of atmosphere hundreds of kilometers above the cloud tops, and that layer stayed warm, absorbing and trapping energy at wavelengths it would not normally retain, for years. The planet absorbed the storm's energy into its stratosphere and held it. The occurrence interval of roughly 29. 5 years is tied to Saturn's orbital year, the time it takes to complete one circuit around the Sun. The mechanism connecting the orbital period to the storm's trigger appears to involve the slow seasonal changes in how sunlight heats different parts of Saturn's atmosphere over the course of a full year. As the northern hemisphere transitions from winter to spring and receives more direct sunlight, the thermal gradients in the atmosphere shift in ways that once per Saturn year create the conditions for the deep convective eruption. The timing is not perfectly regular. The interval between Great White Spot years has varied historically, but the correlation with the Saturn year is strong enough that the events are considered periodic, tied to the planet's own seasonal calendar rather than to any random trigger. The next Great White Spot will come. Saturn's seasonal cycle does not end because no one is watching for it. There is no surface to land on. This is not a statement about Saturn being inhospitable or poorly equipped for visitors. It is a physical description of what Saturn is. There is no ground. There is no transition from atmosphere to solid rock that a spacecraft or a human being could reach and stand on. The planet is gas all the way down, and down keeps going, and what the gas does as it goes deeper is one of the most extreme transformations that matter undergoes anywhere in the solar system. At the level of the cloud tops, where the temperature is around minus 178 degrees Celsius, Saturn looks recognizable as a gas atmosphere. There are clouds of ammonia ice crystals at the highest levels, and water ice clouds somewhat deeper. The chemistry is not breathable, and the temperature would kill quickly, but the physical conditions, pressure slightly above what Earth's atmosphere has at the surface, gas behaving as gas, are at least within the range of things we can describe in familiar terms. Descend further. The pressure rises at a depth of roughly 1,000 kilometers below the visible cloud tops. The pressure reaches levels comparable to the deepest ocean trenches on Earth. At 10,000 kilometers down, the pressure is roughly 100,000 times what you experience at sea level. At these pressures, hydrogen begins to behave differently. The gas, which exists as individual molecules of two hydrogen atoms bonded together, starts to compress into a liquid. Not a gradual thinning of the line between gas and liquid, but a transition into something that flows and moves like a liquid, under conditions that would require technology we do not yet possess to create even on a laboratory scale. Descend further. At around 30,000 kilometers below the cloud tops, something stranger happens. The pressure reaches a threshold, roughly 3 million times atmospheric pressure at Earth's surface, at which liquid hydrogen undergoes another transition. The electrons in the hydrogen atoms, which in normal conditions are bound to their atomic nuclei, become delocalized. They can move freely between atoms, the way electrons move through a metal conductor. This state of matter is called metallic hydrogen. It does not exist naturally anywhere on the surface of the Earth. The only places in the solar system where pressure routinely reaches the threshold needed to produce it are inside the gas giants. Saturn contains metallic hydrogen in an enormous layer occupying much of its interior volume, an ocean of it. If ocean is a useful word for a material that conducts electricity and exists at pressures no human technology can currently replicate. The metallic hydrogen layer is also where much of Saturn's magnetic field is generated. The movement of electrically conducting material within the planet's rapid rotation creates the magnetic field that surrounds the entire Saturn system. That field interacts with the solar wind, deflects charged particles, and shapes the radiation environment that everything orbiting Saturn has to contend with. Descend further. The estimates for Saturn's core temperature range between 11,000 and 20,000 Kelvin. The surface of the Sun, by comparison, is approximately 5,800 Kelvin. Saturn's estimated core temperature sits between twice and 3 times that value. What sits at the centre of Saturn is not measured directly. No instrument we have sent has descended into Saturn, and none could. The Galileo probe that entered Jupiter's atmosphere in 1995 survived for 57 minutes before the pressure and temperature destroyed it, and it reached only a small fraction of the depth at which metallic hydrogen begins. Saturn's interior is modelled from how it behaves gravitationally, how it radiates heat, and what physics predicts about matter under extreme pressure. The core is thought to be a dense mixture of rock, metal, and ice-like compounds, but the specifics remain constrained by models, not by any measurement from inside. At the centre of a planet that looks golden and quiet from Earth, the temperature rivals the surface of the Sun. The transition from molecular hydrogen to metallic hydrogen is one of the most studied unsolved problems in high-pressure physics. On Earth, creating the pressures required to produce metallic hydrogen in a laboratory requires extraordinary equipment. The standard approach involves diamond anvil cells, devices where 2 precisely shaped diamonds are pressed face to face with a tiny sample of material between them. The diamonds are the hardest natural material known, capable of withstanding enormous pressures without fracturing. The face of each diamond at the contact point is typically a fraction of a millimetre across, and the force applied to that tiny area through the diamonds from outside produces pressures in the millions of atmospheres. In 2017, a team at Harvard claimed to have produced metallic hydrogen in a laboratory for the first time. The experiment was controversial, the sample was tiny, the pressure conditions difficult to verify independently, and the sample was lost before it could be studied further. The consensus among researchers is that metallic hydrogen may have been achieved, but that the claim is not yet definitively confirmed. Saturn contains it in a layer hundreds of thousands of kilometers thick. The metallic hydrogen layer is not just scientifically interesting as a state of matter, it is the engine of Saturn's magnetic field. As Saturn rotates, the metallic hydrogen rotates with it. The rotating electrically conducting fluid generates a dynamo effect, the same basic mechanism that generates Earth's magnetic field in its liquid outer core, but operating with hydrogen as the conductor rather than molten iron nickel. The difference in geometry between Saturn's field and Earth's field, that near perfect alignment with the rotation axis, may come from something in how the metallic hydrogen layer interacts with the layers above and below it. Some models suggest there is a layer of helium rain above the metallic hydrogen, where helium atoms that were mixed uniformly through the hydrogen during the planet's formation have gradually settled out and are slowly raining downward toward the core. This helium rain would create a conducting layer with different properties than the metallic hydrogen below it, and the interaction between the two layers might explain the unusual field alignment. If that model is correct, Saturn is currently undergoing a process of chemical differentiation that has been running for billions of years and will continue for billions more. The helium that was uniformly distributed in Saturn's interior when the planet formed is slowly unmixing from the hydrogen, sinking toward the core, releasing gravitational energy as heat as it goes. This is one of the reasons Saturn emits more heat than it receives from the Sun. The slow rain of helium is a heat source, gradual and continuous. Saturn is warmer on the inside than the Sun is on the surface. It is generating internal heat at a rate that exceeds solar input, and the mechanism involves a state of matter that we have not yet definitively produced in a laboratory. The descent into Saturn does not have a floor. It has a series of thresholds, each one marking a transition into conditions that belong to a different chapter of physics than the one before. Cloud top to liquid hydrogen to metallic hydrogen to whatever the core is made of at its centre, under pressure we can calculate but not produce, at temperatures that rival stars. There is no surface. There is only the deepening. The rings are not floating. That image of a gentle band of material drifting peacefully around Saturn, sitting still in the solar system the way a wreath hangs on a wall, needs to go. It is the image distance creates. It is not what the rings are doing. The rings are in motion. Every particle in the system, from the finest dust grain to the house-sized boulder, is moving at orbital velocity, the speed required to balance Saturn's gravitational pull. Particles closer to Saturn move faster. Particles in the outermost rings move more slowly. The speed range across the full system runs from roughly 8 km per second at the inner edge of the main rings to somewhat above 20 km per second at the innermost particles near Saturn. 20 km per second is 72,000 km per hour. These are not symbolic numbers, they are kinetic energy numbers. An object moving at orbital velocity carries enough kinetic energy that a collision with another object at similar velocity is not a gentle brush, it is an impact. The physics of what happens when two objects collide at those relative speeds depends on their masses and the angle of impact, but the general outcome is fragmentation, and the fragments then become new particles in the ring system, moving at their own orbital velocities, available for future collisions. Collisions in Saturn's rings are constant, not occasional. Constant at any moment, somewhere in the 280,000 kilometre span of the ring system, particles are impacting each other, breaking apart, redistributing mass, and settling into new orbits. The ring system is not a static structure that formed once and has been sitting unchanged. It is a dynamic collision environment that has been running for somewhere between 100 and 400 million years. In 2017, during the final months of the Cassini mission, the spacecraft performed what the mission team called the grand finale. Cassini crossed through the gap between Saturn's innermost ring and the planet's cloud tops 22 times in its last months, collecting data from a region no spacecraft had entered before. The team pointed Cassini's main dish antenna forward during those passes to shield the more sensitive instruments from ring particles that might cross the spacecraft's path. What Cassini measured in that gap was not nothing. The gap appears clear from Earth, and it is significantly less particle dense than the rings themselves. But Cassini detected material crossing its path. Fine dust. Smaller particles carried by electromagnetic forces. The region between Saturn's innermost ring and its atmosphere is not empty space. It is a zone where the two most dangerous aspects of the Saturn system, the active ring environment and the upper atmosphere's extreme conditions, come within 2,000 kilometers of each other. The F-ring, at the outer edge of the main ring system, is the most visually dynamic part of the structure. It is narrow, roughly 700 kilometers wide, and it is flanked on both sides by small moons called shepherd moons. Prometheus on the inside edge, Pandora on the outside. These moons are close enough to the F-ring that their gravitational pull influences the ring particles on each pass, creating braided structures, knots and temporary channels that form and dissolve over timescales of months. The F-ring looks like a braided rope in some of Cassini's images. A thick strand of material with twisting substrands visible within it. This is what active gravitational sculpting looks like up close. And then there is the dimension that tends to produce a quiet moment of recalibration when you first encounter it. The ring system, all 280,000 kilometers of its width, has an average thickness of between 10 and 100 meters. 10 meters is the height of a 3-story building. 100 meters is roughly the height of a modest skyscraper. A structure that spans a distance wider than the Earth-Moon gap, containing billions of individual objects, all in motion at tens of thousands of kilometers per hour, is in most places less than 100 meters thick. The structure that looks like a peaceful band from Earth is 280,000 kilometers of material moving at orbital velocity, where every object that stays too long eventually breaks. The grand finale of the Cassini mission was designed in part precisely because no other spacecraft had been there, and no future mission would be sent for a long time. For most of Cassini's 13 years in the Saturn system, the spacecraft orbited at distances that kept it safely away from the innermost ring and the cloud tops. The mission was designed for longevity, and longevity required staying away from the most intense radiation zones and the particle environments near the rings. The data collected from those safe distances was transformative. Decades of science about Saturn and its moons would not exist without it. But the inner gap had never been sampled. When Cassini ran low on fuel and the decision was made to end the mission rather than risk contaminating Titan or Enceladus with terrestrial microorganisms after the spacecraft was no longer controllable, the mission team designed a final phase that would use the remaining fuel to spiral the spacecraft inward, crossing through the ring gap repeatedly before the final plunge into the atmosphere. The 22 crossings of the gap provided data from a region that instruments on Earth or from orbit had never reached. Cassini sampled the magnetic field in the gap. It analysed the particle environment. It measured the composition of material falling from the rings into the atmosphere. It detected waves and structures in the ring edges visible only from nearby. And it was destroyed doing so. On September 15, 2017, Cassini entered Saturn's atmosphere at a shallow angle, designed to keep it transmitting data back to Earth for as long as possible before the signal was lost. As it hit the upper atmosphere, the friction and pressure began to heat the spacecraft. The thrusters fired to keep the antenna pointed at Earth against the aerodynamic forces. The instruments continued transmitting. The signal cut off at 7:55 am Eastern Time. The spacecraft had lasted 91 seconds after first contact with the atmosphere. At that point, at 1.5 billion kilometers from Earth, one of the most productive scientific instruments ever built was atomized into the atmosphere of the planet it had spent 13 years studying. The rings it had photographed in such detail continued their orbital motion, unchanged by the spacecraft's passage through them, indifferent to the 13 years of science that had been conducted at their edges. Every object in the solar system has a boundary it cannot cross without being torn apart. Not a conceptual boundary. A physical one. The line is determined by the relationship between the gravitational pull of a large body and the self-gravity of a smaller object approaching it. If a smaller object gets close enough, the tidal forces generated by the difference in gravitational pull between the near side of the object and the far side exceed the object's own gravity, which is what holds it together. When that happens, the object does not survive the crossing. This is the Roche limit, named for the French astronomer Édouard Roche, who calculated it in 1848. Saturn's Roche limit sits at approximately 147,000 kilometers from the planet's center. The main ring system occupies the space between roughly 70,000 and 140,000 kilometers from the center. Those numbers are not a coincidence. The rings exist where they do because they exist inside the Roche limit. Any material at that distance cannot form into a moon. The tidal forces prevent it. Individual particles can orbit, but they cannot aggregate into something large enough to be held together by self-gravity against Saturn's tidal force. This means the rings are not debris from the formation of the solar system that happened to collect in that zone. The rings could not have started as a large, consolidated object in that zone. Any large object that formed there or moved there from elsewhere would have been pulled apart. The rings are what remains of something that came too close. Current models suggest the most likely origin is either a moon of Saturn that had its orbit gradually altered by gravitational interactions with other moons until it crossed inside the Roche limit, or a large comet or external body captured by Saturn's gravity and brought inside that boundary. When the object crossed the line, Saturn's tidal forces broke it apart. The fragments settled into orbits, spread out by collisions and gravitational interactions, and became the ring system. That process happened between 100 and 400 million years ago. The rings we see are relatively young, not ancient history, not a leftover from the solar system's formation 4.5 billion years ago. A recent, in planetary terms, act of destruction. The moon's formation is estimated at roughly 4.5 billion years ago. The dinosaurs appeared approximately 230 million years ago. By that timeline, the rings of Saturn formed sometime in the period after the first dinosaurs appeared and before the mass extinction that ended them. And the process that created them did not stop. Any object that crosses inside Saturn's Roche limit today will not survive. The moon that became the rings did not cross that boundary intentionally or dramatically. Orbital decay is slow. It can take millions of years. But the endpoint for any object that gets close enough is the same. The tidal forces take over. The object comes apart. What remains joins the ring system. Saturn does not collect objects, it disassembles them. The rings are not ancient leftovers from the solar system's formation. They are what remains of something that got too close relatively recently in planetary terms. The Roche limit is named for Edouard Albert Roche, who derived it theoretically in 1848. He was working on a problem in celestial mechanics, trying to understand the conditions under which a satellite could survive in close orbit around a planet. And he developed the mathematics that describes the tidal force balance. Roche's original calculation assumed a fluid, incompressible body, which is a simplification. Real objects are neither perfectly fluid nor incompressible, and the actual Roche limit for any given pair of bodies depends on the density and rigidity of the smaller object. The formula gives different answers depending on whether you are computing the limit for a fluid body, a rigid sphere, or something in between. The rings sit inside the fluid Roche limit for Saturn, which is the most conservative calculation. The concept generalizes beyond Saturn. Every large gravitational body has a Roche limit. Earth has one. If the Moon were somehow moved to within roughly 9,500 kilometers of Earth's center, Earth's tidal forces would exceed the Moon's self-gravity, and the Moon would begin to break apart. The debris would spread into orbits around Earth, and would eventually settle into a ring system around our own planet. That process has happened elsewhere in the solar system's history. The current ring systems of Uranus and Neptune, smaller and less visually impressive than Saturn's, are thought to have formed through similar mechanisms, objects that came too close and were torn apart. Saturn's rings are simply the most massive, most recent, and most visually spectacular example of a process that happens wherever there are large gravitational bodies and smaller objects orbiting near them. The ongoing question for Saturn's ring system is whether any new material will be added to it in the future, offsetting some of the ring rain loss. There are small moons orbiting near the ring system, and some of them are in orbits that are slowly decaying under the influence of tidal forces and interactions with the ring material itself. If any of those moons eventually crosses inside the Roche limit, they will be torn apart and their material will join the rings. That addition would extend the ring's lifetime. How much depends on the mass of the moon involved. The small shepherd moons would add comparatively little. A larger moon would add more. Whether any of this happens on the timescale of the ring's remaining lifetime is unknown. What is certain is that the line Saturn draws at 147,000 kilometers from its center is not a historical artifact. It is there right now. Anything that crosses it today faces the same outcome as whatever crossed it 200 million years ago. The rings are falling into Saturn. This is not a prediction about some distant future. It is a current measurement. Right now, ring material is being lost. The mechanism was measured by Cassini and confirmed by ground-based observation. Saturn's magnetic field generates an electromagnetic environment that charges some of the ring particles. Those charged particles interact with the field in a way that alters their orbital dynamics, and for some of them the interaction directs them inward towards Saturn. They follow the magnetic field lines down into Saturn's upper atmosphere, where they vaporize. The rate of loss is several tons per second. A ton is 1,000 kilograms. Several tons per second means that every second, several thousand kilograms of ring material that existed a moment ago does not exist anymore. It has been incorporated into Saturn's upper atmosphere. Accumulated over time, the models suggest the rings will be gone entirely in somewhere between 100 and 300 million years, depending on how the loss rate changes as the ring mass decreases. That is a long time by human standards. It is not a long time by planetary standards. The solar system has existed for 4.5 billion years. 100 million years is roughly 2% of that history. If the solar system's timeline were compressed into a single day, the rings would disappear in the final 30 minutes. The rings of Saturn, the defining feature of the planet to most humans who have ever looked at a photograph or diagram of the solar system, are temporary, not permanent fixtures, not ancient structure. A temporary phenomenon in the final stages of its existence on a planetary timescale, when astronomers using the next generation of large telescopes look at Saturn in 200 million years, if such observations are made, they will see a different planet. The pale gold disk will still be there, the moons will still be there, at least most of them, but the rings will not. The most recognizable feature in the solar system will be gone. There is a perspective that comes with this that is worth staying with. We are alive during the specific narrow window in the solar system's history when Saturn has full rings. Not the window after the rings formed, but before they reached their maximum extent. Not the window after they began to deplete, but before they became too thin to see. The window when they are present, visible, and still close to their most complete form. Future generations of humans, if they exist in any form, 300 million years from now, will not be able to see what we see when we point a telescope at Saturn. The rings we see tonight from Earth are not permanent. They are a feature of this specific moment in solar system history, and Saturn has been ending them since before our species existed. The ring rain was discovered not by a spacecraft in Saturn orbit, but by Earth-based observations. In 2013, a team using the Keck Observatory in Hawaii published a study based on observations made with the Hubble Space Telescope and going back to original data from the Voyager era. They found that certain narrow bands of Saturn's upper atmosphere were chemically enriched with water and other compounds that matched the composition of ring material. The pattern of enrichment was not uniform across the atmosphere. It followed specific latitude bands that corresponded to the magnetic field lines connecting Saturn's upper atmosphere to the ring plane. The ring material, in the form of charged particles, was following the magnetic field lines inward and falling into the atmosphere along those specific paths. The pattern was the signature of ring rain. Cassini's subsequent observations confirmed and quantified the process. The rate of several tons per second was one of the results from Cassini's final ring-crossing orbits, where the spacecraft was close enough to the inner edge of the rings to measure the rate at which material was flowing from the rings toward the atmosphere. Several tons per second sounds like a large number. At that rate, in 1 year, the rings lose roughly 100 million tons of material. That sounds enormous. But the rings are very large. Early Cassini estimates put the total mass of Saturn's ring system at approximately 15 to 40 times the mass of Mima's, which itself has a mass of about 3.7 times 10 to the 19th kilograms. At several tons per second, the rings lose roughly 1% of their total mass every 100 million years or so. Over 300 million years, that accumulates into a significant fraction of the total ring mass, eventually depleting the rings to the point where they are too sparse to be visible. The rings are going, the physics is running, the timeline is fixed by the numbers. The aspect of this that tends to produce the longest pause when people think about it is not the loss itself, but the timing relative to human existence. Modern humans, Homo sapiens with fully modern anatomy and cognition, have existed for roughly 300,000 years. The rings will last another 100 to 300 million years. Even the lower estimate is more than 300 times the entire duration of our species' existence on Earth. We are nowhere near the end of the rings, in absolute terms, but in planetary terms, we are at the end. The rings formed roughly 200 million years ago when the first flowering plants were appearing on Earth. They will be gone in another 100 to 300 million years. We happen to exist in the middle of that window. Every photograph ever taken of Saturn's rings, by every person who has ever pointed a telescope at the planet, every image sent back by Voyager and Cassini and Hubble, captures the same thing, a structure that exists in the specific geological moment we happen to occupy, and will not be here in the next geological moment. Saturn has more confirmed moons than any other planet in the solar system. As of the most recent confirmation, the count stands at 146. This number has risen substantially in recent years as smaller and more distant moons have been identified with improved telescope technology. For most of astronomical history, the count was in the tens. Then surveys of the space around Saturn using modern instruments began to reveal more and more small irregular objects in distant orbits, each one a captured body, pulled into Saturn's gravitational territory at some point in the past and held there. 146 is more than any other planet by a significant margin. Jupiter, which most people would guess is the moon leader, has around 95 confirmed moons. Saturn's lead is not a matter of counting methodology differences. It is a reflection of how much gravitational territory Saturn holds and how effectively it captures objects that come within range. The moons are not uniform. At one end of the scale sits Titan, which is larger than the planet Mercury, with an atmosphere denser than Earth's and a surface covered by lakes and rivers of liquid hydrocarbons. At the other end are small irregular moons, some of them only a few kilometers across, in distant and tilted orbits that suggest they were captured from elsewhere rather than formed in place alongside. Between those extremes is an enormous variety. Some moons are heavily cratered, their surfaces recording billions of years of impact history. Some are geologically active, reshaped by Saturn's tidal forces from the inside. Some have surfaces of nearly pure water ice. Some are so dark that they reflect almost no light. Some appear to have internal oceans. Each one is a different story about what happens to an object that Saturn holds. What three of them tell, taken in order, is worth understanding in some depth. The largest, the most active, and the one that barely survived. Titan has an atmosphere. That single fact, when it was first confirmed in the mid-20th century, was significant enough that astronomers paid it special attention. Of all the moons in the solar system, only one has a substantial atmosphere thick enough to support weather, and that moon is Titan. Every other moon is bare or nearly so, with at best a thin trace of gas at its surface. Titan's atmosphere is not thin. At the surface, the atmospheric pressure is about 1.45 times Earth's surface pressure. If you were standing on Titan, the atmosphere pressing down on you would be slightly heavier than Earth's. The air would be dense enough to be visible as haze, and it is Titan's atmosphere is thick, with an orange-brown smog of complex organic chemistry that prevented astronomers from seeing the surface at all until radar and infrared instruments could penetrate it. The atmosphere is mostly nitrogen, as Earth's is. That similarity is one of the reasons Titan has attracted sustained scientific interest. But the similarities end quickly. The temperature at Titan's surface is approximately minus 179 degrees Celsius. That is cold enough that water does not exist as a liquid on the surface. Water ice at Titan's temperature is rock hard, as rigid as granite, and is simply part of the geology. What flows on Titan's surface, what fills its lakes and rivers and channels, what rains from its clouds and collects in its low-lying basins, is liquid methane and ethane. The Cassini spacecraft observed Titan extensively, and Huygens, a probe carried by Cassini and released into Titan's atmosphere in January 2005, descended through those orange clouds and landed on the surface. The probe took measurements and photographs during its 2.5-hour descent and for 72 minutes after it touched down. What it found was a surface covered in rounded pebbles of water ice, sculpted by liquid methane flow into shapes that look remarkably like riverbeds and shorelines on Earth. The atmosphere was thick with nitrogen and methane. The temperature matched predictions. 72 minutes. Not because anything destroyed the probe. The batteries ran out. Huygens had not been designed for extended surface operations. It was built to survive the descent and transmit what it found for as long as it could, and it did exactly that. Titan is often described in terms of what it has in common with Earth. The thick atmosphere, the liquid surface features, the active weather cycle, the nitrogen. Those parallels are real, and they make Titan one of the most studied objects in the outer solar system. But Titan shares these features with Earth the way a photograph of a fire shares features with an actual fire. The structure is recognizable. The thing itself is different. A human being on Titan's surface without any protective equipment would not last long enough to take in the landscape. The temperature alone would cause severe frostbite within seconds of exposure and fatal hypothermia within minutes. The atmosphere, while present and pressurized, contains no oxygen. The methane and ethane that fill the lakes and flow in the rivers are not breathable and would be absorbed through skin and lungs in a chemical environment that would begin causing damage before any other factor became relevant. Even in a standard spacesuit, not the kind designed for extreme cold, not purpose-built for Titan, but the kind currently used during spacewalks, the thermal insulation would be overwhelmed by the 179-degree temperature differential. A better designed suit, one built specifically for Titan's conditions, would extend survival time. Dragonfly, a NASA mission scheduled to send a rotorcraft lander to Titan in the 2030s, will explore the surface remotely, without any human body in the equation at all. Of all the places in the solar system that look, at a glance, like somewhere a human might stand, Titan comes closest, and it would be over in minutes. The Huygens probe's descent through Titan's atmosphere took 2 hours and 27 minutes. During that descent, the probe's instruments measured temperature and pressure at different altitudes, sampled the atmospheric chemistry, listened for lightning, photographed the surface through the haze, and transmitted everything it collected back to Cassini, which was passing overhead and relaying the signal to Earth. The images showed a surface that looked, in a fundamental way, like somewhere. Not an alien abstraction, not an entirely foreign landscape that required entirely new categories to interpret. Hills, channels carved by flowing liquid, dark lowlands and bright highlands, the same geomorphology of erosion and deposition that characterizes river-carved landscapes on Earth, but made of ice carved by methane. When Huygens landed, the accelerometers recorded a soft impact, like landing on slightly compacted sand or wet clay. The surface material was soft enough to compress slightly under the probe's weight. The probe took its last photographs from the surface, showing rounded pebbles of water ice, smoothed by the same process that rounds river stones on Earth, by liquid flowing over them repeatedly and wearing away their edges. Those water ice pebbles were at minus 179 degrees Celsius. The methane that flows over them, that carved the channels visible from above, is a liquid at Titan's surface, temperatures the way water is a liquid on Earth. The methane evaporates into Titan's atmosphere, rises, condenses into clouds, rains back down, flows in rivers, collects in lakes and seas, and evaporates again. It is a complete methane hydrological cycle, analogous in structure to Earth's water cycle, operating at temperatures that would instantly freeze every water molecule in a human body solid. The largest lakes of liquid methane on Titan, called Maria in keeping with the tradition of naming planetary surface features, are at the North Pole. The largest, called Kraken Mare, has an estimated area of roughly 400,000 square kilometres. It is larger than the Caspian Sea, the largest lake on Earth. It is a body of liquid methane the size of an inland sea. Huygens landed at a latitude of roughly 10 degrees south of Titan's equator, in a region that from orbit appeared to be a relatively flat plain. The images it took from the surface were the first images ever transmitted from the surface of a moon of the outer planets. The 72 minutes it spent on the surface before the batteries ran out represent the complete body of direct surface observation from Titan. Everything else known about Titan's surface comes from orbital radar mapping and imaging, which can penetrate the haze but cannot see detail at the resolution Huygens achieved from the ground. Dragonfly, the NASA mission in development, will change that. The mission involves a dual quadcopter lander, a large drone in practice, capable of flying through Titan's atmosphere, something Titan's thick atmosphere makes possible in a way it would not be on Mars. Dragonfly's planned arrival date in the 2030s will provide the first surface mobility on Titan, the ability to land, study a site, fly to another site, and study that one. What it finds there in the methane rain and the ice pebble rivers and the shorelines of the methane seas will be transmitted back across the 1.4 billion kilometre gap between Saturn and Earth. Titan is not going to become hospitable. The temperature will not change. The methane will not become something breathable. But it will become known in the way only direct surface study produces knowledge in the years and decades after Dragonfly arrives. Enceladus is small. At 504 kilometres in diameter, it is less than 1/3 the width of Texas. In the scale of Saturn's moon system, where Titan is larger than Mercury, Enceladus is not a feature that would automatically draw attention. Early telescopic observations showed it as a bright white object in Saturn's orbit, reflective enough to stand out, but not obviously different in kind from the many other icy moons around the outer planets. Then, Cassini arrived. In 2005, during one of its early close approaches to Enceladus, Cassini's instruments detected something unexpected at the moon's south pole. Material was erupting from the surface. Not volcanic material in the terrestrial sense, not molten rock and ash, but water vapour and ice particles shooting upward from a series of long cracks in the south polar ice, called tiger stripes because of the parallel lines they form on the surface. The eruptions were continuous. Not a single event, but an ongoing process. Plumes of material rising hundreds of kilometres above the surface and spreading into space. The question was what was driving them. Cassini flew through the plumes. This was not a distant observation. The spacecraft passed directly through the erupting material and analysed it with its mass spectrometer and other instruments. What it found changed how scientists think about Enceladus and, by extension, about where in the solar system life might exist. The plume material contained water, salt, silica in a form that suggests contact with liquid water at high temperatures, organic compounds of various kinds, molecular hydrogen, which can be produced by the reaction of water with rock at temperatures high enough to drive chemical processes. The conclusion that emerged from that analysis is that Enceladus has a liquid water ocean beneath its ice shell, and that the ocean is in contact with the rocky seafloor below it, and that hydrothermal activity at the seafloor is heating the water and driving the chemistry detected in the plumes. An ocean of liquid water, a rocky floor, hydrothermal vents generating chemical energy. Those are the conditions associated with the environments around hydrothermal vents on Earth's ocean floor, where life exists at depths beyond the reach of sunlight, sustained entirely by chemical energy from the hot water and minerals venting from the rock. The material Enceladus vents into space eventually spreads out and becomes Saturn's E-ring, the faint and diffuse outermost ring of the main system. Enceladus is actively feeding Saturn. The Moon is producing material that becomes part of the planet. The mechanism that drives all of it is Saturn's gravity. As Enceladus orbits Saturn, the planet's enormous gravitational field pulls on the near side of the Moon more strongly than the far side. This differential force, the same kind of tidal force that produces tides on Earth from the Moon's gravity, squeezes and flexes the interior of Enceladus as it moves through its orbit. The flexing generates heat. That heat warms the ocean. The warm ocean drives the chemistry that produces the hydrothermal activity. The hydrothermal activity drives the plumes. Saturn's gravity is heating Enceladus from the inside. The same force that pulls the rings inward and tears apart objects that cross the Roche limit is simultaneously maintaining a subsurface ocean on a Moon 504 kilometers wide. This is not generosity. Saturn does not differentiate between the materials it is consuming and the processes it is powering. From the perspective of physics, there is no distinction. Gravity applies its rules consistently. The result happens to include both the slow destruction of an ocean world and the conditions that might support life within it. The same gravity that pulls the rings inward is heating the ocean inside Enceladus. Saturn gives with one hand and takes with the other, except it has been taking for much longer. The implications of Cassini's plume analysis for the question of life in the solar system are difficult to understate. Before Cassini flew through Enceladus's geysers, the locations in the solar system considered most likely to host or have hosted life were Mars, with its ancient water history, and Europa, the moon of Jupiter with a subsurface ocean beneath its ice shell. Both of those candidates had been identified based on the presence or likely presence of liquid water and the energy sources that could sustain biological chemistry. Enceladus had not been a primary candidate. It was a small icy moon of Saturn, too far from the Sun for anything resembling Earth-style life. The prediction had been that it would be cold and geologically inactive, a frozen relic. When Cassini discovered the geysers and then flew through the plumes and measured their contents, the situation changed completely. Everything in the Enceladus plumes, the liquid water, the salt, the silica, the organic compounds, the molecular hydrogen from hydrothermal chemistry, matched the list of ingredients associated with the hydrothermal vent environments on Earth's ocean floor, where life exists without sunlight. Not all of those environments on Earth's deep ocean floor have been confirmed to host life, but the ones that do have provided a proof of concept for life, sustained entirely by chemical energy rather than sunlight. And Enceladus appears to have those same conditions, operating at a scale that makes the environment plausibly active enough to sustain chemical processes over geological timescales. The question of whether anything actually lives in Enceladus's ocean is completely open. Detecting life remotely through a plume sample analysed by a spacecraft instrument would require finding something unambiguous, a complex organic molecule with a structure that is difficult to produce abiotically, a pattern of chemical ratios that biological processes produce, something that rules out non-biological explanations. Cassini was not designed for that level of biosignature detection. Its mass spectrometer was capable and returned extraordinary science, but the sensitivity and specificity needed to definitively detect life in a plume flyby were beyond what the instrument was built to provide. A future mission targeted specifically at Enceladus, designed with biosignature detection as a primary goal, is currently being studied. The instruments that mission would need to carry, and the analytical methods that would allow a definitive answer, are subjects of active research. If such a mission is funded and sent, it would arrive at Enceladus decades from now, In the meantime, the ocean is there, the hydrothermal chemistry is running, the plumes are erupting, and the tidal forces that maintain all of it are coming from Saturn, which is itself 1.4 billion kilometers from Earth, a golden point of light in the night sky that most people associate with stillness and beauty. Mimas almost did not survive. Of all the moons in Saturn's system, Mimas is the one that looks most like evidence. Not evidence of beauty or complexity or active geology. Evidence of what happens when the Saturn system delivers a large impactor to a small moon, and that moon has just barely enough structural integrity to hold together. The moon is 396 kilometers in diameter. It orbits Saturn closer to the planet than any of the other major moons inside the main ring system, at a distance that keeps it within reach of the ring particles and the tidal forces and the overall density of gravitational influence that characterizes the inner Saturn system. Its most prominent surface feature is a crater called Herschel, named for William Herschel, who discovered Mimas in 1789. The Herschel crater is 139 kilometers wide. On a moon that is 396 kilometers in diameter, a 139 kilometer crater represents more than a third of the moon's total width. It is not a small impact feature on a large surface. It is a scar covering a substantial portion of a small world. The walls of the crater are around 5 kilometers high. The crater floor has a central peak rising roughly 6 kilometers, the uplifted material from the impact that rebounded after the initial compression. The whole structure is visible clearly in Cassini's images, and it gives Mimas an appearance that has made it recognizable in popular culture for a reason entirely unrelated to science. The impactor that created Herschel released an enormous amount of energy in a very short time. Models of the impact suggest that an impactor slightly larger, or moving slightly faster, or striking at a slightly different angle, would have crossed the threshold from leaves a very large crater to shatters the moon. Mimas survived because the impactor was on the edge of what the moon could absorb. Not comfortably within that threshold. On the edge. If Mimas had been destroyed, its material would have joined the ring system. At that time, roughly 4 billion years ago when the crater formed, the inner solar system and the Saturn system were both subject to a much higher rate of large impacts than they are today. Mimas carries the mark of that period on its face. What Mimas tells us is not subtle. The Saturn system has a violent impact history, and that history is written on the surfaces of the moons that survived it. The moons that did not survive are part of the rings. The crater on Mimas is 139 kilometers wide. The moon survived. But it carries the record of what the Saturn system does to objects that pass through it. Saturn's magnetic field is unusual. Most planetary magnetic fields are tilted at some angle relative to the planet's rotation axis. Earth's magnetic field is offset from its rotation axis by roughly 11 degrees. Jupiter's is tilted by about 10 degrees. The tilt is expected. It is a natural consequence of the way planetary dynamos work, with the convecting conducting material generating a field that is not perfectly aligned with the rotation. Saturn's magnetic field is tilted by less than 0.06 degrees. It is, within the precision of our measurements, perfectly aligned with the rotation axis. This alignment should not be stable according to the standard models of how planetary magnetic fields are generated. A perfectly symmetric dynamo, in theory, should decay over time rather than maintain itself. Saturn's magnetic field is obviously maintaining itself, which means either the current models are missing something about how Saturn's interior works, or there is an asymmetry in the deep interior that is too subtle to detect from outside. The answer is unknown. What is known is that the magnetic field Saturn generates is about 600 times stronger than Earth's, and it creates a magnetosphere that extends millions of kilometers into space, forming a protective bubble around the entire Saturn system that deflects much of the solar wind. Inside that magnetosphere, charged particles accumulate in radiation belts. Saturn's radiation belts are fed by several sources: particles from the solar wind that penetrate the magnetosphere, particles shed from the ring system, and ions released by the surfaces of Saturn's moons. Enceladus contributes significantly, as its plumes inject material into the magnetosphere that then becomes part of the radiation environment. The radiation environment in Saturn's inner system is not as extreme as Jupiter's. Jupiter's radiation belts are among the most intense in the solar system, capable of damaging spacecraft electronics and delivering lethal radiation doses to unshielded humans in a matter of hours. Saturn's belts are comparatively less severe. Comparatively less severe still means lethal to unshielded biology. The distinction matters for mission planning, but not for survival calculations. Cassini, which was a heavily instrumented scientific spacecraft built to withstand the radiation environment it was entering, experienced degradation in its instruments over its 13 years in the Saturn system. The cumulative radiation dose altered the performance of various sensors and required adjustments to how the spacecraft operated as the mission progressed. Cassini was designed for this. A human being or a spacecraft designed for Earth operations without additional radiation hardening would not last 13 years. The radiation does not reach Earth, but Saturn's reach extends much farther than radiation, and it already has. About 3.9 billion years ago, something changed across the inner solar system. The Moon bears the clearest record of it. The surface of the Moon is covered in impact craters, a geological record preserved for billions of years by the Moon's lack of atmosphere and geological activity. When scientists analysed the rocks brought back by the Apollo missions, they found that a disproportionate number of the major lunar impact features dated to a relatively narrow window of time, clustered around 3.8 to 4.1 billion years ago. This period is called the Late Heavy Bombardment, and the geological evidence for it is not limited to the Moon. Mars shows a similar pattern. Some of the oldest rock formations on Earth, and portions of the crust that have survived long enough to retain their ancient chemistry, carry chemical signatures consistent with an elevated bombardment rate during that same period. The question was why? The inner solar system is thought to have formed around 4.5 billion years ago, and the standard expectation is that the rate of large impacts would have declined steadily as loose material was swept up by the planets in the first few 100 million years. A sudden increase in large impacts nearly 600 million years after formation does not fit a smooth decline. The leading explanation is called the NICE model, developed in 2005 by a team of planetary scientists, and it places the cause of the late heavy bombardment in the outer solar system. The model proposes that in the early solar system, the giant planets did not occupy the same orbits they hold today. Jupiter, Saturn, Uranus and Neptune were arranged differently, more closely spaced, in a configuration that was initially stable, but not permanently so. Over time, the gravitational interactions between the giant planets and the disk of smaller bodies in the outer solar system gradually shifted their orbits. At some point, Jupiter and Saturn reached an orbital configuration where Saturn's orbital period was exactly twice Jupiter's. This is called a 2.1 orbital resonance. When this resonance was reached, the gravitational interactions between the two planets amplified dramatically. Saturn's orbit shifted. That shift sent gravitational disturbances through the outer solar system that destabilized a vast reservoir of smaller bodies. Comets and asteroids that had been in stable orbits for hundreds of millions of years were knocked onto new paths that carried them inward. Many of them ended up in the inner solar system. Some of those impactors struck the moon. The craters in the lunar highlands, the large and overlapping basins that dominate the moon's near side, date to this period. The mare basalts that filled many of those basins afterward were the result of volcanism triggered by the impact heating. The entire visible geography of the lunar surface, the geography that humans looked at from Earth for all of recorded history and walked on in 1969, is substantially the product of impactors delivered there 3.9 billion years ago. Some struck Mars, some may have struck Earth, though Earth's geological processes have erased direct surface evidence. Saturn's role in the NICE model is not peripheral. Jupiter and Saturn together drove the resonance event. The gravitational architecture that caused the late heavy bombardment was a product of how the two largest planets interacted. Saturn's gravity was one of the two forces that reshaped the inner solar system's impact history. That reach is not theoretical. It is written on the moon's surface. It is in Earth's early geological record. The gravitational architecture Saturn maintains continues to shape the orbital structure of the solar system. The mean motion resonances between Saturn and other bodies still influence how material moves through the outer solar system, which pathways long-period comets follow, which objects are eventually perturbed toward the inner planets, and which remain stable in their distant orbits. Saturn's gravitational influence is not contained within its ring system or its magnetosphere, or even the orbits of its 146 moons. It extends across the solar system, and it already has touched Earth in ways that shaped the world we live on. The craters on the moon are not random. Some of them are there because of where Saturn was in its orbit 3.9 billion years ago. Saturn's reach did not stop at its rings. The NICE model has been modified and refined since its original publication in 2005. The original version required the giant planets to have been in a specific initial configuration that some researchers found difficult to reconcile with other aspects of how planetary systems form. Subsequent versions of the model have adjusted the starting conditions and the sequence of events to better match a broader range of observations about the early solar system. The late heavy bombardment itself is also a subject of ongoing research. Some scientists have questioned whether the clustering of impact dates seen in lunar samples reflects a true spike in the impact rate, or an artifact of how the moon's geological history has been preserved and sampled. The Apollo missions landed in specific regions of the moon, and the rocks brought back represent a sample from those specific locations. If those regions were disproportionately affected by one or a few large impacts during the proposed bombardment period, the sample might overrepresent that period. The debate is not resolved, but the mainstream view among planetary scientists remains that some form of late heavy bombardment occurred, that the impact rate in the inner solar system was elevated around 3.8 to 1 billion years ago, and that the gravitational dynamics of the giant planets played a role in causing it. The implications extend beyond the craters we can count on the moon. The late heavy bombardment is thought to have delivered significant quantities of water and organic compounds to the inner solar system from the outer regions. Comets and asteroids from the outer solar system, where water ice and organic chemistry were more abundant during the solar system's formation, were redirected inward. Some of that material reached Earth. The proportion of Earth's current water inventory that arrived during the late heavy bombardment versus earlier periods of accretion is debated. The isotopic signature of Earth's water, specifically the ratio of ordinary hydrogen to deuterium, is used to compare Earth's water against the water signatures of different populations of comets and asteroids. The ratios suggest Earth's water came from multiple sources over different periods of the planet's history. but some portion of Earth's water arrived late, delivered by the gravitational dynamics that Saturn was a part of. The water in Earth's oceans, the water that makes up the majority of a human body, the water that has supported every living thing that has ever existed on this planet, includes material that arrived here because of where Saturn was in its orbit 3.9 billion years ago. The reach did not stop at the rings. It reached here. Saturn does not intend any of this. That is worth stating clearly, not as a philosophical qualifier, but as a factual one. Saturn has no agenda. It does not move its magnetic field to trap charged particles out of hostility. It does not generate the hexagonal storm because it is trying to create something alien and difficult to explain. It does not pull its rings inward because it is consuming itself. It does not heat Enceladus's ocean and then pull the material from that ocean into its E-ring because it is making a complicated gesture about creation and destruction simultaneously. It does all of these things because it has 95 times the mass of Earth, a rotation period of 10.5 hours, and the physics that apply to any object of those dimensions applies to Saturn. What we call the rings is what destruction looks like when it organizes under gravity. An object that came too close was torn apart, and the material spread into orbits. And gravity sorted those orbits into bands, and the bands are visible from 1.4 billion kilometers because they reflect sunlight efficiently. The beauty is not a coincidence, it is what those physics produce at those scales. What we call the hexagonal storm is what fluid dynamics produces when it has enough mass and enough rotation and no land to interrupt the flow patterns. The hexagon forms because at Saturn's rotation rate and atmospheric conditions, the wave pattern that develops at the polar boundary locks into a 6-sided standing structure. This is the same physics that produces hexagonal patterns in fluid dynamics experiments in a laboratory on Earth. Saturn is running that experiment at planetary scale. What we call the Great White Spot cycle is what happens when seasonal heating slowly builds a thermodynamic instability in the deep atmosphere until it erupts. Saturn's year is 29, 5 Earth years long, which means the build-up time is long and the release is correspondingly large. It is a pressure valve. The scale is enormous. The mechanism is straightforward. What we call the Roche limit is simply the boundary where Saturn's tidal forces exceed the self-gravity of any approaching object. The boundary does not move. The rule does not change. Any object that crosses it will not survive. The hexagonal storm has been running since before humans walked on Earth. The rings have been collapsing since before our species existed. The late heavy bombardment that Saturn contributed to happened 3.9 billion years before any living thing on Earth was aware of what was happening. Saturn was not waiting to be discovered or understood. It was simply running at the scale physics allows. We are the part of the story that looked. From one small planet at a distance of 1.4 billion kilometers, using instruments we spent centuries developing, we worked out what the hexagon is, why the rings are organized the way they are, how the interior transitions from gas to metallic hydrogen, what drives the storm cycle, how Enceladus got its ocean, and what Saturn's gravity did to the Moon 3.9 billion years ago. We looked at Saturn from 900 million miles and worked out what it was doing. That is not a small thing. The sky tonight looks the same as it did before we began. The same stars, the same darkness between them. And somewhere in that sky, if the night is clear and you know where to look, a golden point of light that holds its position with the patience of something that has been there for billions of years. What you know now about that point of light is different. Saturn right now has winds moving at 1,800 kilometers per hour at its equator, and that is the baseline. the condition the atmosphere maintains when nothing unusual is happening. The hexagonal storm at its north pole is rotating, each side wider than the diameter of the Earth, its walls holding their geometric shape by fluid dynamics that we can model but still do not fully understand. Somewhere in the deep atmosphere, the next great white spot is building pressure along a cycle timed to the planet's own year. The rings are collapsing inward at several tons per second. The same magnetic field that maintains the radiation environment is pulling charged ring particles down into the upper atmosphere, and the rings will not be there in 300 million years. We are in the specific window of solar system history when they exist in their full form. Enceladus is erupting water vapour from its south pole right now, as you listen to this, feeding material into the E-ring and maintaining the ocean inside it through the same tidal forces that are slowly disassembling the moon from within. 146 moons are orbiting a planet whose gravity has already reached across the solar system and changed the surface of the moon that rises over our own night sky. The teams that analysed Cassini's data are still publishing results. The spacecraft ended its mission in 2017 when it was directed into Saturn's atmosphere, a final plunge designed to prevent contamination of Titan or Enceladus with terrestrial microorganisms. The data it collected during 13 years in the Saturn system will continue to be analysed for decades. The Dragonfly mission, a rotorcraft lander, is in development and projected to reach Titan in the 2030s to study its surface chemistry and atmospheric conditions directly. We do not have a spacecraft capable of surviving Saturn's full radiation and pressure environment long enough to study the interior directly. We do not have a direct sample of the ring material. We do not have a measurement of Saturn's core that is not derived from modelling. We do not know the precise mechanism that maintains the hexagonal storm's geometry against the turbulence around it. This is not pessimism, it is precision about where the boundary sits between what we know and what remains open. What we have is this: every measurement we have been able to make points in the same direction. Saturn is what physics builds when it runs without the constraints that make Earth a livable place. The pressure limits that keep our atmosphere at a survivable density are absent on Saturn. The temperature equilibrium that maintains liquid water on Earth's surface has no counterpart inside a planet whose core rivals the Sun's surface in heat. The quiet that characterizes a clear night from the surface of Earth, the calm between wind gusts, the stillness of an undisturbed lake, those are conditions that require very specific and unusual circumstances that most of the solar system simply does not provide. Saturn shows us what the default looks like. The base, what you get when you have enough mass and enough time and no particular reason for anything to be gentle. And from 1.4 billion kilometers at the right angle, with sunlight catching the rings and the golden haze of the cloud tops reflecting light back across the distance, it looks like the most beautiful thing in the solar system. Both of those things are true. The beauty is not, it is what those physics look like from here. The rings are organized destruction seen from a distance at which the destruction is not individually visible, and the organization dominates the image. The gold of the cloud tops is scattered sunlight filtered through a hydrogen atmosphere running at speeds that would strip apart anything we could build or carry. The system as a whole, the rings and the moons and the storms and the magnetic field and the tidal forces and the gravitational reach, is Saturn existing as Saturn at the scale physics made available. If you find yourself outside on a clear night and you know where to look, find it. A steady golden point. Not flickering the way stars do, holding its position in the sky with the patience of something that has been there for 4.5 billion years. What you are looking at is a world where the hexagonal storm is running, where the rings are falling in by a few tons every second, where Enceladus is erupting right now above a subsurface ocean that Saturn's gravity keeps warm, where 146 moons orbit a planet that once sent impactors across the solar system and left their marks on the moon above your head. It looks calm from here. It always has. Now you know why. If tonight's time with Saturn stayed with you, share it with someone who has ever looked up at that golden point of light and wondered what it really is. And if you want to keep exploring nights like this one, we will be here. Good night.